Okay, so DIS structure function, the OPE. Now we have to put everything together and write the OPE for deep elastic structure functions, which means writing the OPE for the hadronic tensor, right? So let me erase this. And OPE for DIS. Okay, so we are writing our hadronic tensor, which remember was twice the imaginary part of the proton matrix element of the product of two currents. And then we just treat this product of two currents using the OPE, which we've just seen, which means that this is then written as twice the imaginary part, and then this guy here, basically. So we have a sum over n of coefficients Cn of q square times 2p dot q divided q square. And then you'll ask, well, okay, but if I want to determine these guys here, I have to find out which operators I'm talking about. So what are the leading twist operators in QCD? You know, I'm not going to write the QCD Lagrangian. You know that it's a non-abelian gauge series with fermion fields called quarks interacting through a non-abelian SU3 color gauge interaction mediated by a spin 1 field called gluon, and then you see that the leading twist operators are in fact twist 2 operators, so twist is equal to 2, and for fermions, so for quarks, they are bilinear operators which have the structure psi bar gamma mu 1 d, where, well, d mu 2 d mu n psi, where d mu is a covariant derivative minus I e a mu. And the twist of these operators you can immediately calculate as being equal to 2, because let's see, the dimension of an operator like this is the dimension. You remember probably that the dimension of a fermion field in units of mass is 3/2. So this is a fermion bilinear, which you can remember, remembering that a mu J mu has dimension 4 because it's like a terminal Lagrangian, and the gauge field has dimension 1, so this guy must have dimension 3, but it's bilinear, so this is 3/2, so 3 plus 3, and then you have 4, which is, 3, and then you have each of these d's is carrying dimension 1 because it's a derivative in units of mass. So it's 3 plus n minus 1, because you have n minus 1 derivatives, minus n, and therefore it's 3 minus 1, which is 2, okay? And you can easily see that you cannot construct charge conjugation, even because we are forgetting parity violation, Lorentz covariant operators out of fermion fields that have lower twist than these ones, okay? And you have a similar tower of operators for gluons, which I'm not going to write for lack of time. And therefore, what I'm sticking in here in place of these O mu operators are these guys here, the twist 2 operators. And then when I take the matrix element of these guys in the proton, I take the matrix element of these guys in the proton, and then I have to pull out factors of momentum, which are, you know, the p mu's here, and what remains is the scalar matrix element, which is then the matrix element of this operator, having extracted all the tensor structure. Okay, now here on the left-hand side, I have J mu, J nu, so I have a, I'm constructing a rank 2 tensor. And then I have to decide which of the momenta are carrying the indices mu and nu. And I have two possibilities. Either I decide that the index, that the mu and nu momenta are carried by p's from this matrix element here, or else that they are carried by q's from this guy here, okay? Both possibilities are there, and according to which of the two I choose, I'm going to get the Wilson expansion for one or the other structure function. So here, really, on the right-hand side, I have the sum of two contributions. One contribution where I have p mu, p nu, and then all the rest, and the other where I have q mu, q nu, and all the rest. Okay, so I'm going to write the one with p mu and p nu, and the other one. So if I have p mu and p nu, that means that two of the indices of the operator here are carried by the p's, and the rest are the mu1s, mu-n's that are carried by the derivatives here. Okay, so this means that in this particular case, then here I get p mu, p nu, and then 2p dot q now here is raised to the power k minus 2, n minus 2, n minus 2 because two powers of momentum are carried by the p's here, and I want to match my overall dimension here, and then I have my coefficient, my scalar coefficient an down here, right? And then I have another term where instead here I have q mu, q nu. Okay, so this means that because I'm calling the coefficient of p mu, p nu the F2 structure function, okay, this means that my F2 structure function, F2 of x and q squared, so now I have to compare, so here I really have plus dot, 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 right? All the terms with the q's and so on. I focus on this. I compare it to the expression of the W mu nu with F1 and F2 that I had a few blackboards ago. And I called the coefficient of P mu, P nu, I called it F2, right? Up to a factor of x, because there was a 2p dot q divided by q squared. So this means that F2 of x and q squared is what is written up there, twice the imaginary part, sum over n, Cn of q squared, and then I have 2p dot q divided by q squared, in fact, to the power n minus 1, and not n minus 2, because if you remember in the definition of F2, I had introduced an extra factor of 2p dot q divided by q squared. That's kind of historical. There is no deep reason for that, but that's what people do. And then I have my operators. So I'm calling the summation index n, so my operators here are an, okay? Now, you immediately see that this guy here, so 2p dot q divided by q squared is 1 over x Bjerkane, right? 1 over x, the variable on which this guy depends. So you have this factor here. And at this point, using Cauchy's theorem, you can more or less easily prove that the imaginary part of this guy here is actually equal to, so in order to determine the imaginary part of this guy here, you have to look at the analyticity structure of this. And you see here you have 1 over x to some power. So you can extract the coefficient of 1 over x to some power by Cauchy integration about the origin. And then you deform the integration contour. You realize that there is a cut on the real axis in 1 over x that starts from 1. So you're doing a kind of integral over x. There is a cut on you're doing an integral about the origin in order to extract the coefficient here. You deform your integration contour. You pick up the contribution from the cut. You take the imaginary part. And then you can actually show that the nth contribution from here, so the coefficient of n minus 1 here, is actually given by an integral. So you can show that let's say, Cn q square an, so the term that multiplies this thing raised to the power n minus 1, is actually equal to the integral dx from 0 to 1 of x to the power n minus 1 of f2 of x divided by x. Okay? Yeah, so the idea is you extract the nth coefficient by contour integration, and this is then equal to the corresponding integral on the left-hand side. Okay? So this is the crucial relation which will lead to factorization for deep inelastic scattering. So this is the final outcome of this relatively complicated calculation. And the nice thing here is that the integral which is being done here can be thought of as an integral transform, which, as you probably all know, is called Mellin transform, which is basically the same thing as a Laplace transform, provided you change variables from x. So this is Mellin transform, which is a transformation in x, which corresponds to a Laplace transformation in psi defined as log 1 over x. So if you change variables from x to psi, this is just a Laplace transform. And this means in particular that f2 of x over x can be written as the inverse transform of this guy. And the inverse transform of this guy is like the inverse Laplace transform. I don't know how familiar you are with Laplace transformation, but you know, it's like a Fourier transform with less an I, which means that when you invert it, you have an integral over a contour in complex space, so it will be an integral over n now, from c minus I infinity, c plus I infinity of x to the minus n of Cn q square a n. Okay, so you can actually get the structure function from an inverse Mellin transform of the product of the Mellin moments, as they are called. They are moments of, you know, moment integrals of your function. By thinking of, so, you know, here n was an integer value. It was the number of derivatives. It was you know, the dimension or the spin, the number, the rank of the operator. But nothing prevents you from analytically continuing this, first of all, to the whole real axis and then to the whole complex plane. And you just think of this guy. You know, if you're calculating this with Feynman diagrams, you'd get some expressions which you get from computing with actual operators, which you can then analytically continue for any value of the moment variable. And then you're integrating in the complex plane of n, real n, imaginary n, over a contour which is from minus I infinity to plus I infinity, and which you take sufficiently to the right that it's to the right of all singularities of the integrand. And you know that for any reasonably behaved function, this must exist, because just look at this guy here. This is like exponential of minus n, so this is like exponential of minus n log 1 over x. So for sufficiently large n, this will be an exponential suppression, and therefore, you know, any function will be integrable provided n is sufficiently large, unless the function is totally crazy. This is called convergence abscissa of the Laplace transform, and you know, if you don't remember it, you can even look it up in Wikipedia. It's fairly well explained. So you just go to the right of all singularities and you integrate like this, and then you can close your contour if you wish. Yes. Yeah, good question. I put n and not n minus 1 because when I change variables from x to log 1 of x, I get an extra, so d psi is dx over x. Yeah, so the 1 over x, so I'm thinking of this like this. Yes. Here white is n minus 1 because one of the tensor indices is carried by the gamma. Gamma is dimensionless. So the -1 is because all these are dimensionful, but the gamma is dimensionless. So this is, yeah, because this is this is the dimension which was called dn, I guess, and this is the spin rank. Okay. The dimension, yes, yes, yeah, sure. Of course, the total dimension is this. Now I was thinking about the dimension of the guy that stands in the middle, and then I have 3, which is carried by the 2 fermion fields. Okay. So I'm computing the twist of the operator. Yeah, sorry. This I said D, but this is really T. Yeah, this is twist. So the twist is the dimension, which is 3 plus n minus 1, because it's 3 halves n minus 1, because this is plus 1, and then minus n, which is the rank of the operator. Okay. More questions? Okay, very good. So, yeah, back to my final result, which is written here. So I can get my structure function as the inverse Mellin transform, so this contour integral here of the product of the coefficients times the reduced matrix elements. And at this point, I can actually use a powerful result, which is the Mellin transform version of the convolution theorem for Laplace transforms. So you may be, if you did some differential equation course, you may remember the convolution theorem for Laplace transforms, which you prove by just doing an integral and changing variables. And I'm going to write its version in terms of Mellin transforms. So the convolution theorem tells us that if you have 2 functions, so let's say you have one function f of x, of which you calculate Mellin moments dx, x, n minus 1, which you call big F as a function of n. And then you have another function, g of x, of which you can calculate, again, Mellin moments integral from 0 to 1 dx, x, n minus 1, and you call this g of n. Okay, then it turns out that the inverse Mellin transform of the product of Gn Fn, so inverse, so this is an integral dn from dn c minus I infinity, c plus I infinity, x to the minus n. This is equal to a function h of x, where h of x is the convolution of f and g, which means the integral dy over y from x to 1 of fx over y gy, which by changing variables you can show to be completely the same thing, as you may imagine, because everything is symmetric in f and g, as the integral dy over y g of x over y f of y. Okay, so the inverse Mellin transform of a product of 2 Mellin transforms is the Mellin transform of a convolution function. And this convolution is sometimes written as f and then this kind of symbol times g, which then, of course, is a function of x. Right, so the functional dependence goes through this kind of weird combination, which will have a physical interpretation. So for now, this is just mathematics. By the way, you might be amused to know that all this was discovered by Parisi, who actually noticed this result And then he said, well, there is an interesting mathematical theorem, which is the convolution theorem for Mellin transforms, such that I can actually write this expression for the structure function as a convolution. And then he said something like, this has no clear physical interpretation, but it can be useful in order to analyze the data. And then the physical interpretation came later, and I'm going to show you the physical interpretation in a second. So for now, what we conclude is that this equation here, immediately using the convolution theorem, which I just wrote up there, so that's just mathematics. This means that f2x divided by x, f2x. So, I can use this result by saying, well, my function f is the coefficient function whose Mellin moments are Cn, and my function g is the thing whose Mellin moments are the reduced matrix elements, and the product function is the structure function. So what this is telling me is I can think of the structure function as being the structure function divided by x, because there is this annoying factor of x which is there for historical reasons, as the convolution of something which I want to call C. By abuse of notation, I also call it C of x convoluted with, let me call it Q of x, where I'm defining C of x as the inverse Mellin transform of Cn, and Q of x as the inverse Mellin transform of An. So this is just a definition for the time being. So I'm defining C of x as integral dn C minus I infinity, C plus I infinity, x to the minus n sorry, I wrote C of x. I should really write C of x and q squared, because my Cn's were functions of q squared, right? So this is really C of x and q squared. Cn of q squared. And this guy, so the guy whose Mellin moments are the Wilson coefficients for leading twist operators, is called a coefficient function. This is called coefficient function. And of course, you remember in the beginning we had two structure functions, and I only wrote the result for one because I picked one tensor structure. In fact, we'll have different coefficient functions according to which of the two structure functions I'm looking at. Also, I'm cheating because I said there are only these operators. Well, first of all, in QCD there are many flavors of quarks, as you know, so I'll have a different operator combination according to how many flavors I have, and also I can construct leading twist operators out of gluon field operators. So I really will have a coefficient function for each quark, a coefficient function for the gluon, and two different coefficient functions, one for the structure function F2 and the other for the structure function F1, which are related in some way, which I don't have time to discuss now. So by saying I have a coefficient function, I'm kind of slightly oversimplifying things, but for what I want to discuss, this is more than enough, okay? So the coefficient function is the inverse Mellin transform of the Wilson coefficients of the leading twist operators, which for me are those operators. So it's just one tower of operators, okay? And then I define Q of x as the inverse Mellin transform of the reduced matrix elements. So my A n's, the reduced matrix elements, remember, are nothing but the matrix elements of the operators, reduced in the sense that they pulled out the factors of p mu. But other than that, they're just matrix element of operators. This guy here is called the PDF, parton distribution. So in QCD, the parton distribution is the inverse Mellin transform of the analytically continued whole space of the matrix elements of leading twist operators. Okay, this is how you define the PDF. And actually, John Collins and collaborators have shown long ago that you can actually define the PDF directly as a matrix element in X space. You don't have to go through Mellin moments and then take an inverse Mellin transform by defining a suitable Fourier transform at the level of operators. So what John Collins has shown is that you can actually write this. Let me write the full expression, which is a bit lengthy, but it gives you the flavor. as an integral dy minus, you see in a second why I call it y minus, of exponential minus I x. X is Bjerken x, the same Bjerken x I have here. P plus y minus. Y minus is just an integration variable, which I'm calling y minus, times a proton matrix element of a bilinear and bilocal operator. So psi bar, so the same psi bar which I have here, but then evaluated at a point which is 0, y minus 0. So I'm writing, so this is a space operator, so it's psi bar, it's a field defined in position space, which therefore depends on 4 coordinates, which I write in a light cone basis. So, you know, sum and difference of energy and momentum, and then the transverse part. And this is evaluated with one light cone coordinate different from 0, with respect to which I'm Fourier transforming, and all the other components of the momentum equal to 0. And then I have a Wilson line operator. So I'm sorry, here I have a product. I'm continuing the expression on the next line. It's too long to fit in one single line. So I have a path-ordered exponential of an integral dy minus bar, which is just an integration variable going from 0 to y minus times a gauge field A plus of 0, y minus 0, 4 vector. I'll explain the notation in a second. Psi just evaluated at point 0, matrix element in the proton. Okay, so what I'm doing here is I'm taking the matrix element in the proton of a bilinear operator where I have psi bar and psi, so I have 2 fermion fields, evaluated at 2 points, which are the same point with respect to 3 coordinates and a different point with respect to 1 light cone coordinate with what is called the Wilson line operator, so an integral between, you know, the 2 points at which the 2 field operators are evaluated over the component of the gauge field, which makes a scalar product with respect to the space component, which is giving non-zero separation between the 2 fields. Okay, so I'm taking A plus y minus because the scalar product of A plus and y minus is non-zero. The reason why I wanted to write this expression, so one can prove that if you just take a Taylor expansion of this guy here with respect to the separation, then you get the tower of operators over there. You just expand it, Taylor expand it. You know, when you Taylor expand it, you get out powers of x mu and the derivative because that's a Taylor expansion, and that gives you the operators. So you can prove that actually this bilinear guy, once expanded, is the same thing as the inverse Mellin transform of the operators. The reason why I wanted to give you this is because you're going to have the lectures by Dean Alexander about PDFs on the lattice, and what they do on the lattice is evaluate this guy here. Okay, so it's useful to have in mind that the moments of the operators on the lattice, well, sometimes on the lattice they actually evaluate the moments of operators, but more recently and more in general, they try to evaluate the bilocal operator directly, which on the lattice is kind of complicated because of the light cone separation, and I'm sure that Dina will tell you lots of things about it. But just keep in mind that this is an efficient way of writing directly in momentum space the inverse Mellin transform of the leading twist operators. Okay, so this actually defines something which is going to lead us in a second to the parton model, even though this might be surprising. So I think in my, so like this, I finished the chapter OPE for DIS. The OPE for DIS allows us to write the structure function as a convolution of a coefficient function times a parton distribution, where I define them respectively as inverse Mellin transform of Wilson coefficients and operator matrix elements. So next chapter is getting the parton model out of this. And then the next chapter, which I may not be able to do today, will be to actually get the full-fledged QCD factorization out of this. So parton model. How do we get the parton model out of this? So what do we parton model? this is something that John Collins gets very upset about because, sometimes people say, well, the parton model is that thing where you assume that any physics process can be described by having an incoming quark that carries a fraction x of the parent proton momentum. And, he says, well, why? Who says that? Where does this come from? Doesn't make any sense. And he's right because, is some kind of ingrained folklore, which, however, can be derived rigorously, and I'm going to show you how to do that. So John Collins likes to derive it directly from this formula, which is more complicated, but it's also more general, because then you can do it for any process, not just for deep inelastic scattering. For deep inelastic scattering, we are saved by the Wilson expansion, and then things become rather easier. And the idea is the following. The idea is that, if you look at the top part of the blackboard, you see that what I did was to use the Wilson expansion for the product of two currents, whose matrix element is evaluated in a proton state. But remember, the Wilson expansion is universal. So if I take away the proton bra and ket from both sides of that expression, everything else is true in any state, right? So, if I take away P right and left to the left-hand side of the equation, and also in ANs I take away P and I just write the operator, that's true in any state. So I might as well evaluate both sides of the operator in a state where I can calculate things. Probably in a proton, I don't know the wave function of the proton, but I can evaluate both sides of the equation in a free quark state. Why not? Then I can calculate everything, and then by comparing the two sides, I get the Wilson coefficient. And the Wilson coefficient is universal because it's a property of the Wilson expansion. So that's the idea. So the idea is that I evaluate both sides of the equation in a free quark state, and then I have to ask myself, very good, where's the dependence on the free quark state on the right-hand side? It's on the reduced matrix elements, right? So I need to know what are the reduced matrix elements for a free quark state. So let's say I take a free quark with momentum p, and I evaluate, let's say the simplest operator which I can have, which is psi bar gamma mu d nu psi. This is the simplest because I need at least two vector indices to make up the two currents mu nu. So the lowest dimension one I got is the one with just the two indices. Now this guy you will recognize, by the way, as the fermionic part of the energy momentum tensor. This is it's the energy momentum tensor up to remaining tensor structures. It's the energy momentum tensor of the quark. So this is energy momentum tensor of quark. Of course, the energy momentum tensor has the extra bits, but I'm simplifying, the G mu nu, the subtraction of the trace, but I'm simplifying the tensor structure, as you know, okay? And so this is P mu, P nu, and if you actually evaluate it with properly normalized fermionic fields, that's what it is. That's P mu times 1. So in a free quark state, for a free quark, this would be A2, is equal 1. And in fact, if you properly normalize your operators, you can define them in such a way that all ANs which appear up there are all equal to 1 in a free quark state. Well, if you're wondering how does this happen, well, you know, in a free quark state, psi bar and psi are just free Dirac spinors, u bar u, and then you just use the Dirac equation, right? And d mu is like p slash, and then you just get p nu. Okay, so you just use the Dirac equation for a free fermion field, and then you find that all ANs are equal to 1. Now, if all ANs are equal to 1, then now go and look at here. This means that in the convolution here, the PDF has disappeared, right? Because that's just equal to 1. So this means that the coefficient function, so what do I get from my factorization formula when I set all ANs, i.e. the coefficient function is equal to 1? Well, I get that Cn, without AN, because Cn of Q square, it would be times AN, but AN is equal to 1. So AN, which goes away because it's equal to 1, is the nth moment x n minus 1 of f2 of x over x. Or otherwise stated, f2 of x over x is the coefficient function c of x and q square. But you say, hang on, but which f2? Well, f2 when I take a free quark target, right? Because what I've done here is to say I replaced the proton state with a free quark state. This means that my original DIS process, instead of being deep inelastic scattering over the proton, is deep inelastic scattering over free quark, right? And then I just go through my whole song and dance, and I discover that the structure function of a free quark is the coefficient function, or conversely, what the coefficient function is the structure function on a quark target. Okay, so this is what in QCD factorization is sometimes stated as the statement that what the coefficient function is a partonic cross-section. By partonic cross-section, one means a cross-section in which you take the target and you substitute, instead of having a proton, you replace it with a parton. Now here, it's not a parton, it's just a quark, because I've cheated and I said that there is only one tower of operators. In actual fact, I would have both quarks and gluons, and if I had introduced the gluon twist operators, then I would have that I have the quark coefficient function is the structure function on a quark target, the gluon coefficient function is the structure function on a gluon target, which would be a little more complicated, but the same idea. So the big result that we found is that the coefficient function is the coefficient function for a quark target. Okay, so what is the coefficient function of a quark target? The coefficient function for a quark target, of course, is something that I can calculate by calculating Feynman diagrams. Now, at higher and higher order in perturbation theory, that might be more or less complicated, and the guys who recently computed next to leading order coefficient functions and anomalous dimensions actually calculated deep inelastic scattering on a quark and gluon target up to 4th order in alpha S. But if I do it at leading order, it's very, very, very easy because it's just kinematics. At leading order, Q, P, so I'm sorry for the bad notation. Q here, I mean the Q of my very first blackboard, the momentum transfer of the momentum of the virtual photon. P, I mean the momentum carried by the quark, okay? And this here gives P plus Q, but P plus Q is a free quark, so it's something that squares to 0 because free quarks, well, we are considering light quarks, of course. Heavy quarks would be a little more complicated. But then this means that, P square is also equal to 0. So this is just 2p dot q minus q square, and this is equal to 0, which means that, remember that I had defined x as q squared divided by 2p dot q. So this tells me that x is equal to 1. So the coefficient function the leading order coefficient function, so C leading order x and q square is actually just delta of 1 minus x up to some normalization, which is some number which I can define to be equal to 1. So, there's some normalization up front, which will depend on how I normalize things. I'm doing it in a somewhat rough and ready way. You can sit down and do it more carefully with a Feynman diagram and so on. But at the end of the day, it's just kinematics. So the cross-section for scattering of a virtual photon on a free quark is just the Dirac delta functions. Okay? Now, this is at leading order. Beyond the leading order, the coefficient function is something non-trivial, and I'm going to discuss it in a second. But before I do that, let me just show you what happens at next leading order. So at next leading order, I will get that F2. So hang on. Let me stick to the leading order first. I was forgetting something important. So if the coefficient function is a delta, then what do I get when I substitute this in my factorization expression, which is still here? I get that F2, so this is leading order, that F2 leading order of x and q square divided by x is the convolution, so it would be the integral dy over y from 0, 1 of c of x over y times q of y, but c of x over y is now delta of 1 minus x over y, and this you just substitute, you take, you change variables, this kills the y here, and then you discover that this is just q of x. So the leading order structure function is the parton distribution. And this is what is called the parton model. The parton model is that thing where now Bjerken x, which is a physically observable variable, is the argument of the parton distribution. Okay, and now you'll say, but what about the momentum fraction? Okay, let me show you that. No, I want to erase this. So let's see what happens beyond leading order. So let's say next leading order. Now, at next leading order, the coefficient function will be some more complicated function, a non-trivial function, which I'm going to discuss later on. So for the time being, let's just say that now the coefficient function is of c of x and q square. Notice that here there is no q square dependence simply because everything is trivial. The kinematics has collapsed. At higher order, the q square dependence will reappear, as we'll discuss tomorrow at this point. So at next leading order and beyond, I have some non-trivial structure, and then the structure function f2 of x, always divided by x, is equal to an integral dy over y, x and 1, c x, y, and q square, q of y. Now, let me write down explicitly what this c of x over y is. So I can write it as integral dy over y from x and 1. Now, remember, x is Bjerken x. So this is q square divided 2 p dot q. And then there's a little y here. And then q of y. So you see, if I look at this coefficient function here, this coefficient function is now a coefficient function in which I replaced momentum p by momentum y times p, okay? So p has been replaced by y times p. So this guy here is the cross-section for deep inelastic scattering of a virtual photon over a quark whose momentum is y times the momentum of the proton, okay? Yes? Y is an integration variable. It was defined by the convolution theorem of Mellin transforms. You remember, this guy here is the convolution of the inverse Mellin transforms of these two guys. So it's just an integration variable. And then I see that this integration variable here appears in such a way that the coefficient function is just the cross-section for scattering of a virtual photon on a quark that quote-unquote, carries momentum fraction y of its parent proton, which means a quark whose momentum is y times the momentum of the proton, times the PDF q of y, which is, quote, you know, among quotes, a probability or, a weight that I'm giving to the cross-section here. So my structure function is a weighted cross-section in which I take the cross-section for scattering on a proton, on a quark that carries momentum fraction y of the proton, weighted by the PDF y, which is not quite a probability because q doesn't have to be positive semi-definite, it could be negative, so it's not really a probability, but it's sort of a probability, okay? And by the way, so this is what, this is the parton model, if you wish. So this is the QCD derivation of the parton model, which tells me why, sorry for the pun, is the momentum fraction, and in which sense Q is the probability of having that momentum fraction. And by the way, notice that interpreting Y as this momentum fraction probability is completely consistent with the interpretation of Q as the thing whose moments are matrix elements of operators, because, so this is really the parton model, if you wish. And notice that the integral dy from 0 to 1 of y times q of y. Okay, I'm calling it y, I could call it x, it doesn't matter, it's an integration variable, is the Mellin moment, 0, 1 dy y to the n minus 1 q of y with n equal 2. So it's the matrix element of the spin 2 operator. So this is actually remember, the Mellin moments of the PDFs are the matrix elements of the operator. So this is the reduced matrix element of the operator psi bar gamma mu d nu psi up to a tensor structure carried by, it's a reduced matrix element. So the tensor structure is really, this guy is A2, if you wish, and this guy here is P nu A2. And then you see this is the energy momentum tensor. And this is the total momentum, because it's the probability of having momentum fraction weighted by the momentum. So having interpreted y as a momentum fraction is completely consistent with the fact that its integral, its second moment, is the matrix element of the energy momentum tensor. So it's really the momentum fraction. It's not just that it looks like the momentum fraction. And this is, if you wish, the naive parton model. Why naive? Because there is no q-square dependence. Everything is independent of q-square. And it's, in some sense, what you get from the stupidest leading order QCD calculation, having done factorization properly, and this is probably a good place to stop. And okay, I'm going a little slower than I wanted, but that's fine. And what I want to show you next is then how to, so there are two more steps to go. So here I derived the naive parton model. The next step is the so-called QCD improved parton model, which will still be leading order, but it will be a leading order in which now the q-square dependence starts appearing. And then, by going one little step further, we get full-fledged QCD factorization. So we have two more steps. Naive parton model, which we've done, QCD improved parton model, which is leading order but with q-square dependence, and general factorization, okay? And this will probably take me the first hour tomorrow, and in the second hour, I'll tell you something about actually determining PDF, so putting back all the complicated structure where you have both quarks and gluons and different kinds of quarks, and you want to disentangle different things. You have experiments with uncertainties, theory uncertainties, experimental uncertainties, and we could go on forever. Questions? Okay, there have been a few questions during the discussion. Yes?
You said that in general, if you consider the oscillators, you have 8 of these functions, and they are different for any structure function, right? So first of all, I want to know that they are different for different functions. Secondly, why 8?
Okay. How many independent coefficients and structure functions I would have? So first of all, everything has to be multiplied by 2 in the parity conserving case because I have 2 structure functions. Okay, so I would have F1 and F2. Actually, at leading order, I would discover by doing the explicit calculations that at leading order, so in the naive parton model, they are actually proportional to each other. And you can sort of guess, because here there is a kinematics argument, and then, you know, according to whether I factor out a P or a Q, typically there will be a factor 2P dot Q between them. And indeed, you discover that the F2 structure function and the F1 structure function at leading order are just related by a factor 2x. But this is not true. This is just because leading order is pure kinematics, if you wish. By the way, a little comment that I should have made before, but thanks for the question. Very old people that you may or may not meet, because at this point they are all retired, used to call parton distribution structure functions. So there are many people, many older guys who say structure functions, and they really mean parton distributions. And this is because in the very beginning, you know, in the 70s or 80s, when, you know, just before even my times, there was only the naive parton model. And in the naive parton model, as we've just seen, the structure functions are the same thing. Well, you know, structure function is the same thing as the parton distribution. So for very old people who are who were young in the 70s, so are typically 80 years old now, structure function and parton distribution are synonyms. But sometimes, I'm mentioning this because sometimes, well, first of all, you see it in old papers. And also sometimes some people keep repeating it, maybe they're, even if they are not 80 years old, because they heard it from other guys and they keep repeating it. Okay, so the F2 and F1 structure functions are the same at leading order, but that's kind of accidental. That's called the Calan-Gross relation, by the way, but okay. And then, how about the coefficient functions? So first of all, you can immediately see that if I had a gluon target, at leading order, the coefficient function would be 0 because a gluon is not electrically charged. So in order for a virtual photon to interact with a gluon, I need at least to create a QQ bar pair. So if I say leading order, meaning 0th order in the QCD coupling, the gluon coefficient function is 0 and the quark coefficient function is a delta at leading order. So quark and gluon are already different, and then of course at next to leading order they will both be non-zero and different. Then what about different quark flavors? Okay, so in principle in QCD I have 2NF quark flavors. So, I have 6 quarks and 6 antiquarks, so I have 12 in principle coefficient functions. This is something that I wanted, if I have time, I wanted to discuss tomorrow because that starts getting to the problem, how many independent PDFs do I have? But let's say, just to give a short answer, let's say heavy quarks, where by heavy I mean quarks whose mass is bigger than the proton mass. Well, so if I define light quarks as well, let's say the nucleon, I can think of the nucleon as the lowest lying bound state because the pion is a different business because the pion is a Goldstone boson, so the pion doesn't count. And then the scale of the lowest lying states is the mass of the proton, and then I call heavy anything that is bigger than that scale, and light anything that is lower, and therefore I have 3 quark flavors that are massless in the sense that their mass is not relevant when I do scattering on bound states because it's lower than the mass of the bound states. And then in that sense, I have 6 PDFs. And then I have 7 because I have up, down, and strange quarks and antiquarks and the gluon. Okay, and that's what I have. And the heavy ones are different because then I have different dynamics in which the mass of the quark enters, and and then many things which I said and I'm going to say tomorrow would no longer be true because of quark mass effects. And then you can ask, are these 6 Q and Q bar coefficient functions all different? Well, if you go at high enough order, the answer is yes. And they start differing at increasingly high orders. And this maybe I should discuss tomorrow because it started being a little complicated. But let's say that at next to leading order, so at leading order, no, they are all the same actually. At leading order is just 1 quark coefficient function. At next to leading order, you start having 4, and the next to next you have all 6. Short answer.